Down to here. Here's our system of differential equations. We want to practice what we learned last week, which is to rewrite in matrix form, and then we will apply our new learning here and identify some eigenpairs. So I'd encourage you to go ahead and pause this video and rewrite in matrix form. Okay, so if you paused, let's go through. We're just going to write down our matrix form. So we would have y prime is equal to my coefficient matrix, so 1 and 4, 0 and 2 times y. And hopefully you can see where that came from with my coefficients here. So we have our y1s, we have our y2s. Okay, so keep in mind too that, this y prime, this vector function that we did here is interchangeable. If you wrote this as y1 prime, y2 prime, that's totally fine. If instead of y, you wrote that out as the vector function y1, y2, also fine. Okay, that's what each of those are representative of. So we're going to find the eigenvalues of A. Now, the way we do that is we take that formula. Let's find the determinant of A minus the lambda identity matrix and set that equal to 0. So we've got A. Okay, minus the lambda identity matrix, which would just have lambdas on the main diagonal, zeros everywhere else. Okay, so that matrix would look like this. And then the determinant of that, well, and I guess I put that right here. So the determinant of that would look like 1 minus lambda times 2 minus lambda. So we're going to have to do a little foiling here. And then minus 0 times 4, so minus 0. All right, so we've got 1 times 2. We can do that. And then looks like we've got 2 minus 3 times lambda plus lambda squared. So this one is factorable. I'm just going to kind of flip it around a little bit, put it in standard form here. And then my factors would be lambda minus 2, lambda minus 1. Oh, we probably could have seen that one coming, given that that was what we had right there. All right, so that means that our eigenvalues for this problem are lambda equals 1 and 2. All right, so the next thing we're going to do is use the matrix from step 1, and we're going to take these eigenvalues and we're going to look for our eigenvectors. So keep in mind the precursor step before we got this determinant here was we said that A minus the lambda identity matrix times X is equal to 0. That's the fact that we're going to be using here to find the eigenvectors. So we have to evaluate it for each eigenvalue that we found right here. So when lambda is equal to 1, we'll go through that process this first time. So when lambda is equal to 1, keep in mind that my A minus lambda identity matrix, we already found that. It's this matrix right up here. So I'm just going to notate that. This is A minus lambda identity. That's what we want to use down here. So we have 1 minus lambda, 4, 0, 2 minus lambda. And so if we plug in a 1 in place of lambda here, we are going to have 0, 4, 0, 1. All right, now that multiplied by x, so we're going to go ahead and write that vector function as x1, x2. We're going to go ahead and set that equal to 0, which in our case, because we have matrix equation here, would be the 0 vector function, 0, 0 there. This is the part that you're going to be a little uncomfortable with. Okay, once you set this up, so I'm just going to write this here, a minus lambda identity times my x vector is equal to the 0 vector. The part that you're going to be a little uncomfortable with here is that sometimes we have a nice, easy system of equations that we can solve. Sometimes we are just picking an eigenvector that will work for x1 and x2, because it is possible that there's more than one way to write that eigenvector, and that you maybe don't have some solid information like we do in this problem. And what I mean by that is this problem, well, and I guess this one, let's see, because you really don't have a lot of solid information here. This is saying if you take 4 times, well, okay, let me do my matrix multiplication right. 0 times x1 plus 4 times x2 is equal to 0. That's kind of what that first equation would look like, which isn't giving you a whole lot of information except that, okay, x sub 2 could be equal to 0. That's fine. But look, I'm getting the exact same information from the second equation that I could write here. 0 times x sub 1 plus 1 times x sub 2 is equal to 0. So I didn't get any brand new information from that second equation that I could write, which really means that you could pick anything for x1, because if you notice what's happening here, it's getting multiplied by 0. So as long as x sub 2 is equal to 0, according to what we see here, then x sub 1 could really be anything. Now, a lot of times what we'll do is we just default to a 1 or a -1. So we're going to go ahead and set x sub 1 is equal to 1. And we're saying that when lambda, our eigenvalue, is equal to 1, that our possibility for eigenvector here, which we call x sub 1 to kind of line up those subscripts, would be 1, 0. Okay, so to just bring that all together, here's my eigenpair. We say that lambda sub 1 equals 1, and x sub 1 is equal to this eigenvector. Now, what we don't want is to solve for our second eigenvalue and get the same eigenvector. So this is where sometimes a little bit of guessing comes into play, and it's uncomfortable. We don't like guessing in math, but you do have to do a little bit of it here. So disclaimer to you. So let me just go off to the side here and say we go through the same process. So when lambda is equal to 2, I want you to go ahead and pause and give that a try and see if you can come up with what that matrix equation will look like to find our eigenvector. All right, so if you paused and gave that a try, what we would get when we take A minus the lambda identity matrix with lambda equal to 2 is -1, 4, 0, 0. And then here's my x vector, and here's my 0 vector. So if we go ahead and use row 1 there, that's the only one that's going to give us some good information. If we take -1 times x1 plus 4 times x2, we're saying that that's equal to 0. Okay, well, that's fine. 4 times whatever x sub 2 is has to equal x sub 1. So I guess I just pick some x sub 2 and x sub 1 that works for that. Keeping in mind, we can't use what we got for our last eigenvector. So you could go the fraction route here if you really want to. Some people like to stick to whole numbers. So they would say that, okay, I'm going to say that x sub 1 is equal to 4, so that x sub 2 can be equal to 1. But if you said x sub 2 was equal to 1/4, and that makes x sub 1 equal to 1, you're obviously not wrong. The idea here, when I go to do my x sub 2 vector, is again, that I get something different than I got for the last one. But also, if you wrote this instead as 1/4 and 1, or I guess, I'm sorry, flip that and reverse it. If I said x1 was equal to 1, x2 was equal to 1/4, I hope you see that those vectors are just scalar multiples of one another. So that's how we know that even if we don't write our answers exactly the same, we got a good eigenvector, because my answer would just be a scalar multiple of yours. So to bring it back over here, let me go to make this plural, eigenpairs, where lambda 2 is equal to 2, I found my eigenvector was equal to 4, 1. Okay, so last thing here, we already wrote our eigenpairs. Okay, so we're good with that. We want to determine if our solutions form a fundamental set of solutions here. So keeping in mind our initial definition that y is equal to e to the lambda t times x. Okay, now that means that we have to do that for each solution for lambda. So we'll have two components for that. We'll have y1, which is equal to e to the, remember our first value for lambda was 1, so I'll just fill that in here. So 1t times the eigenvector that we found for that solution. So 1, 0. And that y2 is going to look like e to the 2t times our eigenvector 4, 1. Okay, so that means to write out our full solution here for y, we could say that we have e to the t times the matrix 1, 0 plus e to the 2t times the matrix 4, 1. And that this gives us a solution set. Okay, we want to verify, obviously, that it's a solution set, but the way we write this full thing in matrix form is we do our multiplication. So we have e to the t times 1, we have e to the t times 0, e to the 2t times 4, e to the 2t times 1. Okay, so this is my matrix, and if you remember from last week, this is what we called psi, our potential fundamental matrix, made up of our solution here for y1 and y2. Now I know it, hopefully makes sense based on what we looked at last week, that this isn't too crazy. And again, remembering what we learned last week, that if this is the fundamental matrix, that y would be equal to that fundamental matrix times c. So maybe we have an initial value problem, maybe like in this case we don't, okay? But what we're going to do, and I mean, we're not going to do it in this video, but you would check and make sure that the determinant here is not equal to 0, right? So we do the Wronski and we make sure it forms a fundamental set. And then what we'd want to do is go ahead and just take y times c, and, or I'm sorry, the psi times c, which, again, like last week, you could write out like this, times c1, c2. But a lot of times what we'd really try to do is also just simplify that doing the matrix multiplication. So c1 e to the t plus 4c2 e to the 2t. And then we have 0 times c1, and we have c2 times e to the 2t. The nice part about this is it looks like a solution for y1 and y2 like we would have found in our previous units before we were dealing with systems, okay? Because that's really what this is when we write it all out. This right here, the first row, is y1 of t, a solution for this system of differential equations. This right here is y2 of t, a second solution for our system. All right. So that's the big picture. Okay.